number of the sequence, it equals the hash function itself plus some constant multiplied by the step number. So if that was 0, this would be 0, and the whole thing becomes the hash function itself. Okay, and c is a constant. So if c is 1, then we have the sequence where we always go to the next slot. If c was 2, then we go to the slot after the next slot. If c was 3, we have bigger jumps, but always linear, and so on. So linear probing is just probing. All the things we have said about probing, they apply for linear, or they apply to linear probing. The problem with linear probing is the following. Linear probing has a problem called primary clustering. Now, assume with me the following setup. We have this hash table. Okay, we have this hash table. And let's say elements 1, 2, 3, 4, 5, they all map to the same location. And 6, 7, 8, they all map to the same location. Let's say all these elements map to this location, and these elements map to this location. Okay? Assume the hash function is something like that. The hash function is mapping these to that location, mapping the others to this location. Now what happens? Let's say that we are going to insert dictionary numbers or dictionary keys in the following order. 1, 2, 3, 4, 6, 7, 8, 5. So we are going to put 1 because it's free. 2, it's full, so we take the next one. 3, full, and take the next one. 4, full, and we put it here. And then 6, 7, 8. Now what about 5? 5 is going here, and then try until here. So 5 is in a cluster of 5 elements. So it should be that it should take me only 5 steps in the worst case. However, because this cluster unified with this cluster, now I have a bigger cluster. This is a bigger group. This cluster unified with this cluster, now I have a bigger cluster. This is a bigger group, a bigger cluster. So I am forced to insert 5 right here. So I have 7 elements. I have to go through 7 elements before inserting 5, instead of going just through 4 elements before inserting 5. This is called primary clustering. So because I am putting elements next to, linear probing is going to always try next the slots next to the slot where I am trying to where the hash function maps, and the next cluster of slots is going to unify with the current one, in which case it builds even bigger clusters, which is going to affect everything from insertion to lookup to deletion, because next time I need to look up 5, I have to go through all this again in order to find 5. Okay, so this is the problem of clustering. It's called primary clustering, and you see it in linear probing. However, linear probing has got also the advantage of benefiting from the cache. Okay, because remember, when the probing sequence says try this, what is happening in every trial is that we are traveling from CPU to main memory. Or if we have a cache, we are trying to see it in the cache, because this is a location in main memory. If I want to probe, if I have a cache, I will go to the cache and see, is it there? So the first probe, I go to see this location. I will bring, let's say, this part to the cache. So the next probe is for free. It's in the cache. It's very close to me. And 3 and 4. And if I want to probe 6, I have to go back to my memory, let's say, and bring all these guys together. So linear probing benefits from the cache. If it was not linear, if the probing sequence was all over the place, if I probe here, I bring these guys into cache, next time I probe here, well, I have not benefited from the cache. So I bring these people to the cache, which means I evict or I kick out these people from the cache, depending on your cache configuration. So anything which is not linear probing does not benefit greatly from the cache. So there are two things here. I benefit from the cache when I use linear probing. At the same time, there is this problem of clustering, primary clustering. Now, the second form of probing is called quadratic probing. It has a similar equation to linear probing, except that it's a quadratic function. So that means if this is my hash table, it's a quadratic function. So that means if this is my hash table, if I visit this slot, let's say the next one is this one, the next one is this one, the next one is this one. As you can see, the step number or the step size increases. Okay? It's not like linear probing. It's not always close to each other. So the effect of clustering is less severe. I still have to go through lots of things. If 5 keys map to the same location, I still need to go through 5. So, but this is called secondary clustering, but it's not as bad as primary clustering. So the problem of clustering is less severe with quadratic probing. However, it does not benefit from the cache. So linear probing has problem with clustering, benefits from the cache. Quadratic probing doesn't have that big a problem with clustering, but doesn't benefit from the cache. So nothing is really a solution. Reportedly, the best probing mechanism is double hashing. Now, what is double hashing? Instead of using a linear function or a quadratic function, we actually use another hash function. Okay? So instead of using that, we have another hash function. This gets rid of the problem of clustering. But obviously, this can only happen if we choose these two functions here, the original hash function and the helper auxiliary hash function in double hashing, if we both choose them very carefully. If we don't choose them carefully, then our probing sequence is not going to be that great. Choosing them will also necessitate choosing the size of the table quite right. Some schemes use a power of 2 size of the hash table, or a prime number. So every hash function, every probing strategy must be coupled with the right choice of the size of the table, because it's mathematical at the end. You want a hash function, you want the hash function to jump through a table of certain size, so you want to choose the size of the table and the right hash function, so that when you jump through, like when you use a modulus operator, for example, you are going to visit all the cells of the tables with the least amount of collisions and the least amount of clustering. So it's all complicated together. The good news for you is that you don't need to care about these. You don't have to design a hash function or decide on the size of the hash table other than a big size or a small. Decide on the size of the hash table other than a big size or a small size. Usually, you will look at, given your dictionary, you're going to look at the keys, see the keys, what are they, their distribution. For example, we said last time that if the keys are integers, or the keys are people names, or the keys are file names, all these are different things. And you have to choose the right hash function for the right type of keys, for the right problem. Okay? And all this information is available to you. All you have to do is to do a bit of thinking. What is most appropriate here? You have the knowledge. I mean, you will be given the knowledge that choosing this hash function, you have to have a table size prime. Or you have this hash function, you better use a table which has size power of 2. You are using quadratic probing, then you should not let your hash table be full until 50%. Actually, these things are not. These things are true. I mean, these are all considerations for getting expected average case complexity of big O of 1 in hash tables. Particularly the last one, where I say you should not let your hash table become more than 50% full. In order to stop the hash table being full, obviously we need to insert more items. So the only way we do it is to increase the size of the hash table. And this operation is called rehashing. Now, why do we do rehashing? We do rehashing because the hash table, or the complexity of lookup, insert, and delete becomes very bad when the hash table is full, because of the problems of clustering, etc. This is why we do rehashing. So rehashing, what it means is to build a new hash table and copy the elements over. So this is the old hash table, and this is the bigger new hash table. So this hash table is already full. Okay, it's already full. So when I want to make a new insertion, I have to go through all this in order to make it. So the problem to solve, or the solution to this problem, is to have these elements in a new hash table. So they map to different locations according to a new hash function. So next time when I want to make an insert, I have some free space. This is called rehashing. Okay? So I have an old table with keys, and it becomes either full or half full or whatever, depending on the becomes either full or half full or whatever, depending on the probing scheme. There are recommendations that this table should be allowed to be full up to 75%. Or 50%, etc. So I need to build a bigger table. If this has size m, this will be like 2m or more. I have to devise a new hash function. If this was mod m, this is going to be mod 2m, or anything else. It should be a new hash function. We cannot copy elements from here to here. That's not what is rehashing. This is copying. Rehashing means we are reapplying a hash function again. So this is a hash function h. This is a hash function h2. So before putting an element from this table to this table, we have to pass them through the new hash function. So it goes through a new hash function, and the new hash function is going to send them somewhere. Obviously, there is a performance cost associated with rehashing, because we are reinserting everything. We go linearly through this and reinsert everything in the new hash table. However, the cost of this rehashing is cancelled out later on when we do search here. If we keep searching in a table which is like almost full, then every time we do a search, it's going to be linear. Every time we do lookup, we are going to go through everything. If we use linear probing, for example, we go through everything in this table. So if there are like 1,000 cells which are free, and we want to perform 1,000 insertions, for example, it's 1,000 times linear time, because the table is full and we have primary clustering, etc. But if we do rehashing, we are going to spend some time, we're going to waste time. It's a linear time in the size of the table. However, after that, insertions, lookups, deletes, they will be easier, because the table is not completely full, because there are lots of free space, and future insertions are going to be easier. When do we do rehashing? I said it depends. Sometimes when it's half, sometimes when it's full, and you don't have to guess this information. This is related to your hash function and the size of your table. It all comes as one package. If you use closed hashing, then you will have your hashing, your hash function, what size table should work well with this hash function, and what is the exact probing sequence that you have to use, and also when it is a good idea to do a rehashing, and what kind of performance benefit do you expect. This is basically, we are spending a lot of time. It is a good idea to do a rehashing, and what kind of performance benefit do you expect. This is basically, we are spending a lot of time doing rehashing so that in future our dictionary operations are easier to do. Okay. So, the main conclusion of this lecture is hash tables are messy. Okay? They are not as elegant as an AVL tree. However, okay, they don't have performance guarantees. That's something bad about them. However, they have some practical value in some cases. If you have a small dictionary and you want a quick implementation, you don't want to be wasting your time writing the code for AVL trees. If you have done the practical already, you will know how much hassle it is to write code for an AVL tree and balance and etc. I mean, it's a lot of work, but hash functions are easy. If you have a small dictionary, all you have to do is to have a good hash function with a good sized hash table, and try to choose the right size. If you are open hashing, choose a size such that your load factor gives you better performance than AVL, or even if it gives you slightly worse performance, you have saved a lot of time in coding, etc. So hash tables are useful sometimes, but not all the time, and they certainly are not guaranteed for in the worst case. So overall, in this course, we have seen data structures, we have seen algorithms, and now we are able, when we want to program anything, now we are able to think. Is this going to be efficient, or is this not going to be efficient? If you need to program something and you find yourself writing a loop nest of 4 loops, then you know, for example, that this is not going to be good, because it's going to be like n to the 4, big of n to the 4 complexity. You will know also that when you do some divide and conquering, then that's a good algorithm to do. That's a good algorithm because it's going to halve have the steps every time, and you get the log. You always want to show the log somewhere. If you have a dictionary, which you will, almost everything is dependent on a dictionary abstract data type, then you know how to handle these. You know the problems of using an array, or you know the problems of using a linked list or a tree. Why do we balance trees? The other trees we have not seen, in which you will see in the second course of that. We could not see the last lecture on priority queues, heaps, but you will cover it in data structures too next semester, or file organization and processing. So this concludes the course.